Hello. In this video, we're going to be talking about metallic solids, and we're looking at how metallic solids form crystalline solids from the microscopic, so from our unit cell. So metallic solids are a type of atomic solid. So these are going to be solids that are only going to have one atom type. So the whole thing is going to be one atom type. So metallic solids themselves are made of metallic bonds. And metallic bonds themselves aren't just like one bond like we see with covalent bonds, but it is still a sharing of electrons. So with metallic bonds, we consider this what's called an electron C model. And the electron C model basically says we have a bunch of positive ions that are together and they are sharing all of their valence electrons. So positive nuclei, or positive ions, metal ions, in a sea of their collective valence electrons. Okay, more valence electrons usually lead to greater sharing and usually structures that have a little bit higher melting points. But these are things that are metals themselves. We've talked about the structures, but the metals themselves, because of the type of structure they have, that's the reason that they're malleable. That's the reason that they're ductile. So they are malleable, so they can be kind of flattened or compressed and shaped using pressure. They're ductile. They can be pulled into a wire. They are electrically and thermally conductive. And they're going to have variable melting points based on how many electrons are sharing. So it's going to be anywhere from the melting point of mercury, which is negative 38.8 degrees Celsius, to the melting point of tungsten at 3,422 degrees Celsius. So a very, very large range of melting points. In order to melt a metallic solid, metallic bonds must be broken. So the strength of those metallic bonds will determine what type of melting points we see, and the metallic bonds themselves, that strength is dependent upon how many electrons are shared amongst all those nuclei. Okay. So let's real quick look at what the electron C model looks like. So if we think about delocalized electrons, the picture we see on the left, we have our valence electrons around our positively charged nuclei. Our positively charged metal ions. So we have our metal ions with their electrons. With the electron C model, those electrons are going to be shared throughout. So they're not going to be in between specific atoms or specific ions. You're just going to have a sea of electrons with positively charged cations throughout, which is why it's really easy to shape these structures, why we can make them into wires and stuff like that. Because if we were to hit this top area right here, if we were to push it in that direction, there's nothing that's going to stop it from easily sliding past, because we don't have, like with an ionic compound, where we don't have the level of repulsion within a metallic solid. Okay, and we also see within our metals, we get something that's called metal band theory. Because we are sharing all of these electrons, we get an overlap of the energy levels. So the sharing of electrons or the delocalization of those electrons, results in a overlap of the energy levels. And when those energy levels overlap, so we have one, and then we have another, and then another, and another, and as they overlap more and more and more, we get to a point where we form a band of energy levels. And that is what we see in a metal. So we see a continuous bonding area and a continuous anti-bonding area. So we have an area that's full of bonding orbitals and an area full of anti-bonding orbitals, which allow us to conduct those electrons very easily because the filled and the unfilled are basically overlapping with each other. They're right next to each other, so it's very easy to promote an electron from a lower energy state to an unfilled higher energy state. We also, the reason that we see conduction can be seen here as well. So if we have no electrical potential, so if we just have a metal wire, all of our bonding and anti-bonding orbitals are going to be at the same levels, right? So our bonding orbitals will all be at the same level, our anti-bonding orbitals will all be at the same level. But as soon as you add in an electrical potential, so you add in a positive and negative end, or in this case a negative and a positive end, you have an area where you have a negative charge, and you have an area where you have a positive charge. And if you have a sea of electrons, and that sea of electrons can freely move so that we have free movement of our electrons, we're actually going to get a depopulation of electrons right next to the negative charge and a greater population of electrons around the positive charge. So we get kind of this stair-step idea, so we can have a flow of electrons from left to right. Okay, so we're going to shift our energy levels, which allows us to basically move electrons in one direction. And when we can move electrons in one direction, so they'll all be going in that direction, then we can power devices, right? Okay, so metals, they are ductile and they can conduct electrons and they are malleable, all due to this whole electron sea model and this overlapping of all of these energy levels. So with that, let's go ahead and start looking at what type of structures we form our metals. Now that we know what a metallic solid does, let's look at how we form them. So of course, we're going to have a unit cell with our metallic solids, right? So in a metallic solid, we can have one of 4 major crystal packing types for them. It's not all of them, but this is generally the type of crystal packing types we have for metal solids. So our 4 types are simple cubic, or primitive cubic, body-centered cubic, face-centered cubic, or cubic closest packed, and the last one that we look at for our metal solids is hexagonal close packed. Now again, there are other options for our metal solids, but these are the most prevalent and these are the ones we're going to be looking at today. So these are ways that we can take our metal atoms and get them into a packing arrangement. And each of these arrangements are going to have different amounts of empty space and different efficiencies about their packing. And we'll look at that a little bit more later. Our very first one that we want to look at is simple cubic. So this is what the simple cubic looks like. We have a unit cell where we have lattice points on each of our corners. And each of those corner lattice points are shared with 8 different unit cells. So if we have a primitive cubic unit cell, we have a Z number or a atom number equal to 1. So this is how many atoms are in our unit cell. Okay, and it's because we have 8 corners. Each corner has an eighth, and we've already talked about this in a previous lecture, but each one has 8. If we have a primitive cubic, we also have a coordination number for each of our atoms. That coordination number is 6, and we can see that right in this diagram right here, where I've got all the 8 unit cells together. So our nearest neighbors here for a primitive cubic is, oops, not 8, 6. Okay, and we have, so A, B, and C are all the same because we are a cubic cell. So we just call it A. So A is equal to B is equal to C, and A is our cell length, and it is 2r. So we can relate the radius of our atom with our unit cell length. Okay, next one we want to look at is body-centered cubic. In a body-centered cubic, we have points on each of the corners. So we have corner lattice points, and we have one body lattice point. So each of the corners accounts for 1 atom. The body accounts for 1 atom, so we have a Z number for this packing type of 2. Okay, and if we look at this center atom right here, we see that we have 8 atoms around our central atom. So our coordination number in this case will be 8. Okay. And in this case, we have a little bit of space along here that doesn't have atoms. So we actually have an A value that is a little bit different in this case. A is 4r divided by the square root of 3. So that's how we relate a radius of our atom to our A value. And again, this is still a cubic cell, so length equal height. Next one is our cubic closest packed, or face-centered cubic. Okay, here we have corner pieces, and we have face pieces. Okay, the face, as we see from this one, is shared between 2 unit cells. So each one accounts for a half. So we have 6 atoms for our faces. Sorry, 3 atoms for our faces, 1 atom for our corner. So a face-centered cubic has a Z value equal to 4. It is really hard to see in this structure, so I'm going to show you this next structure instead. See if you can see it a little bit better. If we think about this atom right here, right, so we can see this atom right here. It has 1, 2, 3, 4, 5, 6 atoms around it, 1, 2, 3 on top of it, and then it actually has 1, 2, 3 underneath it. It looks like this. And we get from this a coordination number of 12 for our face-centered cubic. Again, it's really hard to see it in this structure, but you can kind of see it in this one where I'm comparing hexagonal to cubic closest packed. Okay. Here again, our edge length is a little bit different than in a primitive. Our edge length will be equal to 2 times by the square root of 2 r. Okay. And last but not least is our hexagonal. Hexagonal closest packed is not a cubic unit cell. So here is what a cubic cell looks like. It has A equals B equals C, alpha equals beta equals gamma being 90. In a hexagonal, which is this one right here, that is our structure for our hexagonal. It has A equaling B, so our A and our B are equal, but our C is different. And then alpha and beta are both 90 degrees, but our gamma is not. It's 120. So it's a little bit offset of a structure. It has a similar packing efficiency to our face-centered. Our face-centered has the highest packing efficiency of 74%. Our packing efficiency for our, and I should have said this earlier, but our packing efficiency for our primitive cubic is like 52%, really horrible packing efficiency, and then body-centered packing efficiency is 68%. So going from our primitive cubic at the lowest packing efficiency, so 52% of that unit cell is filled with atoms. Our body-centered is a little bit better, 68% of the unit cell is filled with atoms. Our face-centered is going to be the great at 74% of the unit cell being filled with atoms. Same thing here with our hexagonal closest packed. It has a 74% packing efficiency. So we have a lot greater percentage of that unit cell filled with atoms. Okay. Here we also, like our cubic, our coordination number here is going to be 12. Right? And then, unlike our cubic closest packed, our Z number here is going to be 2. Okay. Just taking these structures and comparing them. If we have a simple cubic structure, we have basically the same pattern of atoms all the way through. A, coordination number 6, 52% packing efficiency. Body-centered, we have ABA packing efficiency. And then with that, we have a coordination number of 8, 68% packing efficiency. Hexagonal and closest packed are just going to differ in their packing or their stacking pattern. A hexagonal is a little bit simpler. It's an ABA type structure, while with our cubic closest, we have an ABC, ABC. Both of them have a coordination number of 12 and a 74% packing efficiency. And they are, like I said, a little bit different in their structure. They just have, this is a kind of rotating of that layer, which is why you get a different packing efficiency or a different layering effect than you see with your hexagonal. Okay, that's it for this one. See you guys later.